All right, so we're nearing the end of the semester, just one more mini exam left. And it's going to cover all of linear algebra, so I wanted to go back and cover just a few videos on some of the stuff we learned earlier in the semester. So the first of these is determinants. You've probably already gotten really familiar with using them, but in case you wanted to go back and double check your understanding, making just a short video on how to compute determinants with cofactor and also with using row reduction to find your answer. So as we'll see in a second, it's all kind of boiled down to just the 2x2 case. So if we have just an arbitrary 2x2 matrix A, B, C, D, we can take its determinant, which you'll sometimes see written with the vertical bars on the end here. And it's just equal to the product of the diagonal terms, so AD, minus the product of the off-diagonal terms, BC. And this will give you some number. It could be complex, it could be real, but mostly real in this course. And this has a geometric representation, which I find to be particularly helpful. So if we look at these, we can think of the entries of our matrix here, these columns, as just being two-dimensional vectors in the plane. So I have AC here that looks something like this maybe. Again, just arbitrary. And then I have this BD vector here. Maybe it looks something like this. Who knows? And then if I take the determinant of these, what I'm actually doing is I'm finding the area of this little parallelogram that's spanned by the two of these vectors here. So the determinant of A is actually just the area here that's spanned by those two vectors. And we'll actually come back to this because I think it's a useful explanation for the linear independence aspect of determinants. But for now, we'll leave it at that. And if we have a 3x3 case, which is what you see most often on exams and stuff, the same thing generalizes. We can take the determinant of a 3x3 the same way. But what we do is we actually break it up into smaller 2x2s. So what I do is I start, you'll learn, you can actually do it with any row you want, but I've gotten used to doing just the first row. But you pick a row, I'm gonna pick the first row here, and I take a look at my first entry A. I completely ignore my column underneath it and my row to the right of it. And then what I'm left with is this little 2x2 determinant here that I can take. So it looks a little weird if you haven't seen this before, but we do A times this determinant, E, F, H, I. And that forms our first entry here. So what I can do then is I can look at B. So again, I'm just going along this top row here. I can get rid of the row and the column that are along with B, and then I'm left with this little DGFI thing going on in the middle. You put in a minus sign there for some reason. If you want to know about it, check the textbook. But we have minus B times this 2x2 determinant here. And then similarly, we do the same thing with C, and we get our finalized determinant. So again, we take C, we ignore the rest of the row, we ignore the column underneath it, and we're left with D, E, G, H. So we add on to that, plus C times D, E, G, H, and that gives us our determinant. Again, this will be some real or complex number. And just like in the two-dimensional case, there is a geometric analog here. It corresponds to the volume spanned by these three vectors here. And I'm not going to even try to draw it because it's complicated, but there's good diagrams in the textbook if you want to see. Again, we'll come back to this concept here in a little bit. So that's just how to do it with cofactor. Honestly, you'll be using cofactor most of the time. So if you get comfortable mostly with this 3x3 case, you should be good to go for 90% of the determinant problems. But most determinant problems anyway show up with applications. So first and foremost, you've been using determinants for differential equations, which you don't normally do if you learn chapter 4 first, right? Or chapter 3, sorry, because we're going back in time a bit. But you usually use them in applications. So one of the applications of a determinant is that so if A is some combination of column vectors here, and they just span our matrix here. So if the determinant of A is not equal to 0, I should put if here. So if the determinant of A is not equal to 0, then that means that my column vectors here, v1, v2, up through vn, are linearly independent, which is a pretty big property here. So on exams and such, you might come across a problem that looks like this. So if, not if, and you've already seen this on one of your midterms already, but for what values of k is the set v1, v2, v3 a basis for R3? And they give you v1 is 10k, v2 is k11, and v3 is 211. So there are a couple ways of doing it. First of all, you can just solve it out. But the quickest way is just doing the determinant. So you know that if my determinant of these column vectors here, 10k, k11, and 211 is not 0, then those are exactly the cases when you have linear independence among these three vectors here. So you can do this determinant out, and you end up with the relation k squared minus 2k should not equal to 0. You can factor this out. K minus 2 is non-zero. So this tells you that as long as k is not equal to 0, and as long as k is not equal to 2, then you have linear independence among your three vectors here. And since you have three of them, they form a basis for your three-dimensional vector space R3. All right, so that's one application of using cofactor method and this unique property here. Another convenient one that shows up is the fact that you can use row reduction to solve this as well. So if you have a triangular matrix, then your determinant of A just happens to be the product of all your diagonal terms. So A11 times A22 times ANN. So you just go through and you multiply all your diagonal terms together. That gives you your determinant. We're not fortunate enough to have every matrix be triangular, but we know how to get to a triangular matrix. We can row reduce. Unfortunately, and this is kind of tricky, you can't just go through and row reduce and not do anything to the determinant. So every operation you have when you convert A to the row reduced echelon form of A, you have to do something to its resultant determinant. So so if we want to find the reduced echelon form of A, then there are a few things we can do, right? So we can first permute two rows. That's totally fine. We can multiply a row by some scalar k. That's also allowed. And then the last one that we can do is we can add or subtract rows from the other. We can do them one at a time. So one row to or from another. And we saw back in chapter 2 that as long as we follow these three operations, we should be able to get down to the row echelon form of a matrix. And so this is totally fine to do here as well, but you have to change your determinant with each of these. So if you start with a matrix A and you do one operation to it, I'm going to call that new matrix A prime. So A prime then, the determinant of it will change with your operation. And if you permute two rows, you have to multiply by -1. So you start with A, you permute two rows of it, you get A prime, but you have to multiply your determinant by -1. So that's how this is going to work. If you multiply one of the rows by a scalar k, then your determinant of your resulting matrix is just that scalar times your determinant of the original matrix here. And then the cool thing, it's pretty handy actually, is that if you add or subtract rows to another, your A prime is again your resulting matrix from doing that, but nothing changes. You're just left with your determinant of A. So really, you're free to add or subtract rows to and from another without changing your determinant at all. It'll just take a lot of work if you want to try to do it that way. So we're totally welcome to do this. And one of the problems I've seen pop up occasionally, not too often though, and this is just from the textbook anyway, but you're given just an arbitrary 3x3 here. And you're given that your determinant of A is equal to -6. So some combination of, A through I will give you this determinant. They give you another matrix B that is some variation of A. So you've done a lot of stuff to A to get it. G plus 5A, H plus 5B, F plus 5C, and then A, B, and C at the bottom. And based on just this information that they give you here, you're tasked with finding your determinant of B. So since it's arbitrary, you can't use cofactor, right? Because you don't know the numbers. But you can use these properties here and kind of work backwards to figure out what your determinant of B should be. So what we're going to do is we're going to start with A here, and then we're going to go through and perform a bunch of row operations until we pop out B. So if we have A here, if I want to get B, I have to do some permutations first, right? So some of my rows have shifted around. One of these is that the first and the third row have changed from A to B, right? So I have G, H, I, D, E, F, and I have my A, B, C at the bottom, so at least I got somewhere there. But remember, in doing that, I have to change my determinant here. So my determinant of B, A prime, will be -1 times my determinant of A. All right, so by permuting it, I multiplied by -1. I'm going to permute again because I need some stuff in the middle now. So D, E, and F need to go up top, and G, H, I need to go in the middle. So to do that, I permuted rows 1 and 2. And so if I do that, I have to square, or I have to multiply by -1 again, which is the same as just squaring my -1 here. And everything's in the right order now. I just have to do some scalar stuff. So I'm going to multiply my first row by -4. So I have -4D, -4E, -4F, G, H, and I, and then ABC still at the bottom. And I'm getting closer here. I have to multiply by -4 based on this rule here. And then there's one last thing that we have to do to get this matrix here looking like B. I have to add on to row 2 5 times the bottom row. So row 2 becomes row 2 plus 5 times row 1, or row 3, sorry. And some people get confused here, but we'll go ahead and do it so we know we're done, and then we'll look at our determinant. So I have G plus 5A, H plus 5B, and I plus 5C. And then I have A, B, C at the bottom. Sorry, right here, I messed up. This should be an I, not an F. So based off of this, we're finished here. So we've recovered B, but we did this one weird operation here where we added on 5 times a row to another row. And so you might think to yourself, oh, I need to multiply here by 5, right? Because I have a scalar 5 involved. But that's actually not true. So what you're actually doing when you're adding 5 times row 3 onto the middle row, what you're actually doing is you're adding on row 3, and then you're adding on row 3 again, and then 2 more times. So you're just doing step 3 here 5 different times. So you're not changing your determinant at all in doing that. All right, so we've recovered b, so a prime is now equal to b, right, over here. So I have my determinant of b is equal to -1 squared times -4 times the determinant of a, and I know my determinant of a was given to me as -6. So this should give me positive 24. And I'm done. So this is just a couple examples on where you might see determinants on their own in on exams and stuff, and hopefully this was pretty helpful